In this video, we are going to start a new topic, module number 7, related to torsion. Torsion is a moment, but this moment about the longitudinal axis of the member. Let's see this slide. Just a reminder, your member can be under the effect of different types of internal forces. Can be compression force, and this compression force will cause axial stress. Axial compressive stress, sigma equal the applied force divided by the cross-section area. Sometimes your force is tension, but it will cause the same axial stress, but it will be tensile stress, tensile axial stress. Sometimes we have shear force. This will be covered in module number 9. And we have bending. This moment is called bending moment and will be covered in the next module. And right now we are talking about torsion. This torsion is torque on a shaft that will cause shear stress. So previously, in the previous videos, in the previous modules, we covered normal stress. Or to be more specific, we covered axial stress, which is one kind of the normal stress. Right now, we are going to start talking about shear stress, which is coming from torsion. The torsion or twist induced when a torque is applied to a shaft causes a distribution of stress over, not perpendicular, the shaft, the cross-sectional area. So we are in this one, in this case. So if you look to this beam under the effect of this wrench, we are going to apply a force here. This force, besides this length, if you multiply this force by this distance, you can create something called torsion. In a different meaning, it's called torque. So the torsion or the torque is a force time distance. It's a moment. But this moment is rotating about the longitudinal axis of the member. This is the longitudinal axis. So the definition of torsion is the action of twisting or the state of being twisted, especially of one end of an object relative to the other end. So this end will be twisted relative to the other end of the member. Under the effect of torque, I will label it capital T. So this torque equal originally force time distance. That means it's a moment, but this moment is about the longitudinal axis of the member. So this moment rotating about the longitudinal axis of the member, this is the reason why I call it torsion or torque. One of the most common examples of torsion in engineering design is the power generated by transmission shafts. If you look to this motor, this one will create power, will make this shaft to rotate, and then will make this assembly to move forward and transfer the motion to a different part. That makes sense? So we have, this one is related mostly to mechanical engineer, and we are going to explain what is the effect of torsion on a member. Keep in your mind, and which is very important to understand this, torsion will cause shear stress, tau. Torsion will cause shear stress. The value of the shear stress will equal the applied torque, capital T, time radius divided by G. To be honest with you, we are going to discuss the shafts with circular cross-section. Sometimes we have members with different shapes of the cross-section, like rectangle, square, or whatever, but it will be outside the scope of this course. We are going to focus only on the shafts with a circular cross-section. This circular cross-section can be solid or can be hollow. So we have three different parameters that will create or will calculate the value of the shear stress, tau. The capital T is the applied torque, the radius R, the distance from the center of the cross section to any point inside this cross section. J is called the polar moment of inertia. I will talk about the polar moment of inertia very soon, but right now, I would like to highlight a very important point. This value of R represent the distance from the center of the cross section to any point. So here is the center. If you look to this center, the value of R will be 0. Then the value of R increasing. We have a bigger value of R. We have the biggest value of R, which equals C. So capital C or C represented the radius of the cross section. So if you move away from the center, we will have a bigger value of shear stress because we will have a bigger value for R. So if you look to the maximum shear stress tau maximum, I will replace this R with C. And the C represented the radius of the cross section. R in this one is not the radius. R in this expression is the distance between the center of the cross section to any point you are looking for the shear stress at this point. So if you make this radius the biggest value, you are going to get the biggest or the maximum shear stress. And this is the case here. The maximum shear stress, if we have torsion, will be located at the outer circumference of the cross section. So this shear stress distribution, if you look to it for the solid, at the center will be 0. At the outer circumference will be the maximum, tau maximum. And then we will have linear distribution between the two values. 0 at the center and the maximum at the outer circumference. If you look to the hollow shaft, we don't have a material at the center, but at the inner circumference, we will have a value, not the maximum. At the outer circumference, we will have a value which is the maximum value. And in between, we will have linear distribution. Does that make sense? So this is the shear stress distribution in a solid cross-section, hollow cross-section under the effect of torsion. One more time, the maximum shear stress equal the applied torque time radius of the cross-section divided by J. If you would like to figure out the shear stress at a specific point, so that equation will be T, capital T time R divided by J. R in this case is the distance between the center of the cross-section and the corresponding point you are looking for. What you mean by J? J is the polar moment of inertia. If we go back to mechanics, engineering mechanics, chapter of section properties, we learned that if we have a circle with radius R or diameter D, we have something called moment of inertia, Ix and Iy. Both of them are equal in the case of a circle. Ix equal Iy equal pi divided 4 times radius to power 4. or pi divided 64 times diameter to power 4. If we have solid circle, if we have a hollow circle, so it will be pi divided 4 the outer radius to power 4 minus the inner radius. So we have inner radius Ri, and we will have outer radius RO, or inner diameter DI, or outer diameter DO. So if we are using outer and inner diameter, pi divided 64 times outer diameter to power 4 minus inner diameter to power 4. This is the moment of inertia, Ix, which equal Iy for a circle. The polar moment of inertia, which is called J, equal the value of Ix plus the value of Iy. In the case of the circle, equal pi divided 2 times radius to power 4, or pi divided by 32 times diameter to power 4. If we have a solid shaft, solid cross section. If we have a hollow, so pi divided 2 the outer radius to power 4 minus the inner radius to power 4, or equal pi divided 32 the outer diameter to power 4 minus the inner diameter to power 4. So polar moment of inertia J is a section properties equal Ix plus Iy. So before starting, the shear stress, most of the time we are going to talk about the maximum shear stress due to the applied torque equal capital T, the applied torque, time the radius of the cross section C divided by J. That makes sense? So I'm looking for these three values: the applied torque, the radius of the cross section, the polar moment of inertia, if you are looking for a maximum shear stress. But if we have a cross section and this is the center, and I'm looking for what is the shear stress at this point, in this case, your shear stress at this certain point will equal the applied torque time radius divided by G. This R, it's not the radius of the whole cross section, but the radius measured from the center of the cross section to the certain point R. That makes sense? But in the first one, your cross section is here and your center is here, so the maximum shear stress will be located at the outer circumference. So at this one, we will have tau maximum. But in this one, we will have only tau, which is not maximum. That makes sense? Keep in your mind, if we have a solid cross section, this is the centroid, this is the outer circumference, the stress distribution, the shear stress distribution due to torsion will be 0 at the center. We don't have distance, we don't have radius, we don't have R, we don't have C, and will be the maximum at the outer circumference, and in between we will have linear distribution. That makes sense? If we have a hollow cross section, that means we don't have a material inside. So we will have this one and this one. This is the center. So I will have a little value here. I will have a maximum value here. In between, we will have linear distribution. Let's do the first example. The shown solid steel shaft is subjected to the shown torques. We have a torque at A equal 500 pound-feet, at B 900 pound-feet in opposite direction, at C 1000 pound-feet, at D 600 pound-feet. Please make sure you figured out the direction of the applied torque. I don't care it's clockwise or counterclockwise, but if we have two values, each opposite to each other, we have to subtract both of them. Anyway, the shaft has a diameter equal 6 inch. We need to determine the shear stress in each part of the shaft. So before starting, the shear stress, the maximum shear stress in each part of this shaft equal the applied torque times C divided by G. I think the value of C, which is the radius of the cross section, will be 3 inch. Since the diameter of the shaft is a circle with a diameter 6 inch. So the radius will be 3 inch. The value of J, we have a solid cross section. So the value of J will be pi divided by 32 times the diameter of the cross section to power 4. So the value of J will be pi divided by 32 times this diameter to power 4. It will be 127.23 inch to power 4. So I found two values in this expression, C and G. What is the value of capital T? We have to figure out each part alone. So for part A, B in this shift. So in part AB, I'm gonna do cut anywhere in part AB. I have two options. I can use the right side or the left side. It's up to you. But I'm gonna use the smallest one. So I'm gonna use the right part. So here is the right part. I did cut here. And here is we have here this circle at A. And we have applied torque here equal 500 pound-foot. For equilibrium, at your cut, we must have the same value of torque, but in opposite direction to be in equilibrium. 500 pound-foot. That means the applied torque in part AB will equal 500 pound-foot. Actually, I don't care what is the direction or clockwise, counterclockwise. It's not a big deal for shear stress. So the shear stress maximum in part AB will equal T, capital T 500 time radius 3 inch divided by G, which is 127.23. We have a little mistake here because the applied torque is pound-foot. This one in inch. This one in inch to power 4. So all units must be in inch. So I'm gonna multiply this 500 by 12. In this case, everything in inch and the pound. So the shear stress in this case will be 141.5 PSI, which is pound per inch square. That makes sense? Let's do the second part, BC. For part BC. So I am going to make cut in part BC. I will do cut here. We have two options. You can use this part for calculation, or you may use this part in calculation. It's up to you. Both of them will give you the same answer. So I'm gonna use the right part. So the right part, I did cut here. I have a big circle and another big circle. This is A, this is B, and I did cut here. Does that make sense? We have applied torque here 900. And I have applied torque here 500. Yes. So I expect 500 and 900 in opposite direction. So I expect at my cut, I will have a torque moving in the same direction for the 500 with 400 pound foot to make equilibrium. Does that make sense? So the 500 and the 400, both of them will be in equilibrium with the 900. That means the torque in part BC will equal 400 pound foot. That means the maximum shear stress in part BC will equal the applied torque 400 times the radius 3 inch divided by the value of the J 127.23. I will multiply this applied torque by 12 because right now it's in pound foot. I have to multiply it by 12 to be an inch. So the shear stress in this case 113.18 pound per inch square or PSI. The next part CD. So for part CD, I will do cut in part CD. If you did cut here, we have two options. You can use the left part, which is a very little one, or you can use the right part, which is very big. Both of them will give you the same answer. So I'm gonna use the left part. So I did cut here, and I have a big one like this. At D, how much torque here is 600 this way. Nothing else. So, and I did cut here. So I expect a torque opposite to the applied one with the same value 600. So both of them will make equilibrium. So the torque in part CD will equal 600 pound foot. That means the maximum shear stress in part CD, which equal the applied torque 600 times the radius 3 inch divided by J. And keep in your mind, I have to multiply this torque by 12 because it's in pound foot. So the final shear stress in part CD will equal 169.77 PSI or pound per inch square. I don't care about the direction of this torque. It's not a big deal, but we are looking for what is the shear stress, what is the maximum shear stress in the cross section. So this is how to figure out the shear stress in different parts of a shaft. We have one more example. This example has a hollow pipe with outer diameter 40 millimeter and the inner diameter 37. So the cross section looks like a circle, hollow circle with inner diameter 37 and the outer diameter 40 millimeter. So I can say the radius for this one will be 20 millimeter measured from the center to the outer circumference. This is C. And J equal by divided by 32, the outer diameter 40 to power 4 minus the inner diameter 37 to power 4. So it will be 67332. millimeter to power 4. This one in millimeter. So I got the value of C and the value of J because the maximum shear stress equal T times C divided by J. I found the value of C, the outer radius of the cross section, J, the polar moment of inertia. So what is the value of T? So this shaft is supported at A and is under the effect of this applied torque. We need to determine the absolute maximum shear stress developed in the pipe. In which part? This part, I don't know. This part, I don't know. This part, I don't know. So I divided the shaft or the pipe to 3 different parts because we have different torques applied to this pipe. So let's talk about each part for part number 1. At part number 1, I will do cut. This cut will divide your shaft to 2 parts. I'm gonna use the smaller part because the other part will include the reaction at A because it's fixed. I don't know how much is this reaction, so I prefer to use the left part after you did cut. So here is your cut. I did cut here, and we have here applied torque looks like this. How much? 80 Newton meter. So I believe at your cut, I will have applied torque in opposite direction. Equals the same value, 80, to make a chromium. So the value of the torque in part number 1 will equal 80 Newton meter. So the maximum shear stress in part number 1 will equal the applied torque 80 times the radius of the cross section, the whole cross section, which equal 20 millimeter, divided by J, 67,332 millimeter to power 4. This torque is Newton meter, this radius in millimeter, this J in millimeter to power 4. We have to multiply this 80 by 1000 to be Newton millimeter. So the maximum shear stress in part number 1 will equal 23.76 megapascal or Newton per millimeter square. This is for part number 1. Let's do the shear stress in part number 2. So if you would like to figure out the stress in part number 2, I am going to do cut in part number 2. And I will also use the left part because I don't like to use the reaction at E. So in this part, I have this shaft. It looks like this. I did cut here. We have applied torque at this end 80, like this. And I have a torque in opposite direction 20. Like this. Okay. So I expect a torque at the end with the same direction for 80 equals 60. So the 60 and the 20, both of them will be in equilibrium with the 80. That makes sense? So the applied torque in part number 2 will equal 60 Newton meter. So the maximum shear stress in part number 2 will equal the applied torque 60 times radius, which is 20, divided by the G, which is 67,332, But keep in your mind, I'm gonna multiply this torque by 1000 to be in Newton millimeter instead of Newton meter. So the shear stress in part number 2 will be 17.82 megapascal. Let's talk about part number 3. So for part number 3, I am going to do cut in part number 3. And I am also going to use the left bar because I don't like to work with the reaction at A. So I did cut like this in part number 3. Here you go. And this is the shaft. We have a torque here equal 80 applied. We have opposite 20 here. And we have 30 in the same direction of 80. 30, I think. Yes. So we have 80 and 30 in the same direction, 110. Opposite to this direction is 20. So I believe the direction at your cut will be opposite in the same direction for 20 will be 90. So if you look, 90 and 20 in the same direction equal 110. 30 and 80 in the same direction, 110. Both of them will make equilibrium, so the whole shaft will be in equilibrium right now. So 30 and 80 in the same direction will be added together, 110. 20 need help with 90 in the same direction. So the whole shaft or the whole part will be in equilibrium. So the torque in part number 3 equal 90 Newton meter. So the maximum shear stress in part number 3 will equal the applied torque in this part, 90. I'm gonna multiply it by 1000 to be Newton millimeter time radius equal 20 millimeter divided by J, which is 67,332. So the maximum shear stress in this part will be 26.73 megapascal. This is the stress in part number 3, 26. This is the stress in part number 2, 17. This is the stress in part number 1, 23. That means the maximum shear stress will be 26.73 megapascal in part number 3. Keep in your mind, we are looking for what is the absolute maximum shear stress developed in this shaft. We have part number 1, part number 2, part number 3. Looks like part number 3 will be the biggest value of the shear stress. We have one more example. The pipe shown has an inner diameter of 80 millimeter and an outer diameter of 100 millimeter. So this pipe BA or AB has a cross section which is hollow. The inner diameter of this pipe equal 80 millimeter and the outer diameter equal 100 millimeter. If its end is tightened against the support A, it's fixed or supported at A using a torque wrench at B. Determine the shear stress developed in the material at the inner and the outer walls. We are looking for what is the shear stress at the inner, how much, and what is the shear stress at the outer, how much. If this wrench under the effect is rotated under the effect of applied force, 80 Newton force are applied to the wrench. So this hand pushing the wrench up by 80 Newton, and the other hand pushing the wrench down with 80 Newton to rotate this wrench and make or apply torsion to the shaft or the pipe AB. So first step, the value of J for this cross section equal pi divided by 32, the outer diameter 100 to power 4 minus the inner diameter 80 to power 4. This is how to figure out the polar moment of inertia. So 400 to power 4 minus 80 to power 4 time pi divided by 4 will equal very big number. So I can say 46.37 times 10 to power 6 millimeter to power 4. Yes. Okay. What is the applied torque? The applied torque from this wrench equal 80 Newton times 200 plus 80 Newton times 300. Keep in your mind, this 80 Newton times this distance will cause torque this way. This 80 Newton times this distance will cause torque in the same direction. So this is the reason why I added them together to give you the final torque at the end of this pipe. So the final torque will be 80 times, will give you 40,000 Newton millimeter. Keep in your mind, this one in Newton, this one in millimeter. So the final unit for the torque will be 40,000 Newton millimeter. The shear stress at any point originally equal the applied torque times the distance R divided by G. This is the original equation to figure out the shear stress at any point. So the shear stress at the inner wall will equal the applied torque 40,000 time distance R. What is the distance R for the inner wall? It's 40 millimeter. Does that make sense? Keep in your mind, this is your cross section. Let's do it here. So for the inner wall, the radius R or the distance R equal 40. Divided by J, 46.37 times 10 to power 6. I think your units are good. This one Newton millimeter, this one millimeter, this one millimeter to power 4. We are good. Your stress will be 0.035 mega Pascal. Let me repeat it. Yes. For the outer tau, for the outer wall, equal the applied torque 40,000 time the radius for the outer wall will be 50 millimeter divided by 46.37 times 10 to power 6. This stress will be 0.043. So this value of the stress equal 0.035. This value of the stress will be bigger, 0.043 megapascal. In between, we will have linear distribution of stress. That makes sense? So in this example, we learned how to convert the applied force to a torque. Force times distance will give you a torque. Force times distance will give you a torque. Both of them rotating in the same direction. This is the reason why I added them together.